We present Vortex, a virtual reality camera system that records omnidirectional stereo panoramas by spinning fast line sensors. Emerging virtual reality systems offer unprecedented experiences and capabilities for entertainment and beyond. Cinematic VR allows for real scenes to be captured and later replayed. This allows us to travel to distant places and experience remote events up close. However, capturing VR content is not trivial. Conventional panoramas support 360-degree viewing, but do not support stereo content, limiting the sense of immersion. Stereo cameras only record over a narrow field of view, limiting their use for VR. Many consumer electronics companies have recently introduced variants of camera arrays that support 3D capture across all viewing directions. The most widely used format for sharing 360 VR videos is omnidirectional stereo, or ODS. ODS panoramas are multi-perspective projections in which each column corresponds to the perspective of a slit camera. VR camera rigs record high-resolution videos from multiple cameras, shown here for a static shot. Camera arrays record a massive amount of redundant data that requires extensive processing. This involves projecting each perspective onto a cylinder and computing optical flow to interpolate between adjacent views. However, optical flow is expensive and fails for objects that are close to the cameras. Other failure cases include fine details, reflections, refractions, and transparency. To illustrate just how computationally expensive this approach is, consider that every second, the Facebook Surround 360 captures 17 gigabytes of raw data. This is streamed via a fiber optic cable to a dedicated storage rack and then processed in a data center for hours, days, or even weeks. In the end, most of the raw data is discarded, and the remaining pixels are converted into the ODS format. Vortex uses a mechanically rotating camera design that natively records in the ODS format. No additional data processing is required. For high spin rates, the camera is operated inside a clear safety enclosure. The main components of the camera include 2 high-resolution line sensors and 2 fisheye lenses. These are mounted on an aluminum platform attached to a rotary stage. The cameras are interfaced via gigabit Ethernet, and a slip ring allows power and data connections between the stationary and rotating parts of the system. Our system has captured high-resolution VR videos at up to 5 frames per second. Our maximum frame rate is determined by the slip ring's electrical performance. On the supplemental YouTube channel of this submission, you can find a variety of recorded ODS panoramas. Here's a shot recorded at 5 frames per second. The quality settings of these YouTube videos is adjustable up to 4K. Here's another video we captured at a slightly lower frame rate. Slight wobble in the videos can be corrected via hardware synchronization of the motor and line sensors. This was not done for these videos. These scenes cover a 360-degree horizontal by 350-degree vertical field of view. It's difficult to convey in video the sense of immersion offered by these scenes when experienced in VR. When viewed in VR, these scenes offer 3D views over 360 degrees, making them extremely immersive. In this demonstration of live VR, the camera streams 3D stereo panoramas as they are recorded. The screen in the foreground is showing a small subset of one eye's view of the panorama. In the paper, we show how to correct optical distortions from the proposed camera, analyze design trade-offs and signal-to-noise in detail, and propose orientation-dependent rendering strategies that offer temporal seam-free rendering. We compare our system with the Google Cardboard camera app, showing that common distortions and artifacts do not impact our system. Please see the paper for further details. With the proposed VR camera system, we take the first steps towards making VR video capture accessible and enabling live VR streaming.